Good morning, everybody. Welcome to this lecture. Let us quickly recap what we have been doing for the last couple of times. If you remember, we have been basically studying clustering algorithms. That was motivated in the context of game AI by looking at, we came from the problem of path planning. We said there is something like a waypoint graph, which we can use to represent the geometry and topology of a game world. And if we are faced with the problem of programming a character to move in an intelligent fashion from some point A to some point B somewhere in the game world, that poses us with the problem of computing a path. And we saw that there are very powerful algorithms to do that, Dijkstra and A-star. So path planning in graphs is not a problem, but if these graphs are large, then it may run some time. And of course, we want to do everything as efficient as possible. If you were a game programmer, you shouldn't spend too much time on all the AI routines because the physics of the game world has to be computed as well. If you pick up some object and let go, then it has to drop according to the laws of physics, and you have to compute the render, the game world, all the graphic stuff. There's lots of computation going on during a game, so AI typically just gets a tiny slice of the available computing power, so everything has to be efficient. Now, if a waypoint graph is large, then path planning is not so efficient, and our idea was to try to cluster these waypoint graphs, right? Because then we could plan a path from one cluster center to the other, and worry about the details in a subsequent computation step. So this is why we studied clustering. And we talked about k-means clustering, just because everybody knows about this one, and everybody thinks, I'm exaggerating here, everybody thinks that that is the clustering algorithm. Right? There are many more, many more. But this one is arguably the most popular one. It's very easy to understand what it does. It's very easy to implement, and actually there are numerous libraries out there that have implemented it already. So this one is very popular. But we saw that for our purpose, this one might be problematic, right? Because this is a clustering algorithm that is basically considering the geometry of a set of data. In k-means clustering, we do suppose that the data we are given consists of vectors. Two-dimensional vectors, say, for the waypoints in a two-dimensional game world, can be three-dimensional vectors for the locations of the waypoints in a three-dimensional game world. In general, in other settings, that can be any dimensionality, but in k-means clustering, we do assume, tacitly assume, that the data we are given is numerical data existing in the form of vectors. Now, but we have waypoint graphs, so we do know more than just geometry. We actually have an idea about the topology. We just only know like where a waypoint is, but we also know about its neighbors. And so we talked about another approach called spectral clustering, and spent quite some time on this one because this is not as well known as k-means clustering, but in very many problems this is a very good method to use, to consider for application. And in particular, this is because we can think of what spectral clustering does as considering the topology of whatever data we are given. And in this context, when I am talking about topology, what I am referring to is relations. Right? We in a waypoint graph can know that one point is immediately adjacent to another because there is, say, an edge between the two, or it's not quite so adjacent because there are two edges between two waypoints. But these edges define relations. They sort of provide us with a similarity of different points. And of course, K-means clustering, we can compute similarities basically by computing the Euclidean distance. Hey, other distances are possible, but we can compute the Euclidean distance between any 2 points. We would have similarity there as well, but we saw that if we're given a graph where the different vertices may have, I don't know, different numbers of neighbors, where there might be regions in the graph where there are many vertices connected by edges, and then there might be regions in the graph where they are rather sparse because there's, you know, just like one vertex, and just, you know, chain of edges there. These kind of relations among vertices in a graph would be ignored by K-means clustering. But we saw that this approach of spectral clustering is actually able to handle these. We spent quite some time on discussing where this comes from, and we assumed the point of view of a physicist, and saw that this is, in a sense, basically computing standing waves on a graph. And we saw that we can use this just by looking at which vertices behave similar. If there was a wave on the graph, like say all the vertices that are above the ground level would be clustered into one cluster, and all the vertices that are below the ground level would be clustered into the other graph. So this is where this comes from. And today we'll do something exciting, because we will now look at algorithms that combine the best of both worlds. So today we are looking at clustering with respect to geometry and topology. And this will take us back to the area of game AI. When we talked about spectral clustering, we came from the problem of trying to cluster waypoint graphs so as to, for instance, simplify our lives when we are going to compute paths between locations in the game world. And then we talked about this in quite a general manner, sort of moved away from our general topic of game AI. Today, we are going back to game AI. We will look into the problem of learning, what do I say here, topological structures. Topological structures. And another fancy term for this learning of topological structures could also be manifold identification. Manifold identification. Now, there are interesting terms in here we have not looked at so much so far. Learning. And clustering is a form of unsupervised learning. Well, we never really made it very precise so far. And then there is this thing, manifold. Let's look at what we are aiming at today. This is we'll discuss all of this by means of a very simple example. And our application example is the following. And it has to do with game AI. Let us suppose that we are to consider a two-dimensional game map. I'll just draw some map, two-dimensional, I don't know. So we are looking on top of some structure in some game world. This could be some yard, and there's some other rooms, whatever, we don't care. In the exercises, next project, I have already uploaded data files where I have created data from within the game Quake 3, and actually the topology or the geometry of that map somehow looks like this. And in that data, what you'll find is a trajectory of a player who has been playing the game and recording his activities. Well, basically it was me. So I've been playing the game and recorded what I was doing, and all I did was I was running around as the game character in a circle. Right? So we have a game map and a player trajectory. And this takes us back to some terminology we have been discussing at the very beginning of this lecture. We can think of the game map. Let me, this geometric structure the player is moving in as, let me call it a set C, which is the configuration space. Configuration space. And, well, for all intents and purposes in this two-dimensional example, this is, of course, a subset of the two-dimensional vector space over the real numbers. Right? Because we can, I don't know, close this game world now. We don't need this corridor here anymore. It's confusing anyway. So we have a very simple game map. It's a rectangle. And we can think of a coordinate system, I don't know, x coordinates and y coordinates. And therefore every player location, let me single out one of them, has an x coordinate and a y coordinate. And of course, possibly the player, if there are no obstacles, could basically assume any xy coordinate within this rectangle. So every possible configuration, if we agree that a configuration in this context is just a spatial location, is indeed a two-dimensional vector of an x and a y coordinate. Now, in this example, the player did not assume any possible configuration, right? But we have this data set here of actually observed player locations. And let's call this set S. Why would I call it S? If the thing with the configuration space is called C, C for configuration, then what could the S refer to here?
States.
States! Exactly! This is very interesting, right? Remember when we spent all this time about talking about tic-tac-toe. We say, okay, there's possible configurations. We can place X's and noughts on a board. Not all these configurations are valid states. And here we have it again. Right? We have a configuration space. Now it's for a modern video game, say, where a player can move through some world. And every possible location would be a configuration. But this player did not assume any possible configuration, but sort of constrained his movement to a certain subset of the configuration space, which is exactly the same as with tic-tac-toe. Right, where we saw that valid game states are a subset of the configuration space. So S is the state space. State space in this example, and it is, of course, a subset of the configuration space, which again is a subset of the two-dimensional Euclidean vector space. And this term manifold occurs in this context because a situation like that, in machine learning, one often refers to the fact that a set of data one is observing, which resides in some space, but does not really fill that space. In machine learning, such a set of data is referred to as a manifold. this is a bit of a loose terminology, but let's try to understand why it would be used there. Let's see what a manifold typically, what this term manifold typically refers to. So in machine learning, this set S is often referred to as a manifold. And to see why, let us have a brief look at what mathematicians would understand under the term manifold. So let us define that, and I will, again, as this is similar to when I talked about topology, we could make this extremely precise, but that would again take us way too far afield from what we're actually interested in. So I will loosely define that, and then I will discuss this loose definition, and then we have a picture as to what's going on here, and then we can deal with it. Okay? So a manifold is said to be a topological space that locally looks Euclidean. Again, mathematicians would have to take their hard pills now. This is simplifying things a bit, but for our purpose that is okay. What is that to say? What is it to say that a space locally looks Euclidean? Let us try to understand this. Well, again, a very crucial thing is that this planar trajectory consists of two-dimensional points. The state space is a collection of two-dimensional points. They are embedded in a huge two-dimensional plane, but they do not completely fill that plane, but really just are focused or concentrated on some part of the so-called embedding space. And now we have to try to understand what it means to locally look Euclidean. I'll continue this definition here. What does it mean to look locally Euclidean? We can say that for an m-dimensional manifold, and I am calling this object M, manifold M. Well, it could be this sort of circular structure we just saw. Every point X in this manifold, and I'm not using vectors here because we are very general, has a neighborhood, that is, now there is a very fancy term, homeomorphic, and I will not discuss this, to the m-dimensional Euclidean space. I need to fear that this pen is going to leave me. I'll continue in blue, but there's no semantics attached to the change of colors. It's just.
This one looks precise. And
yeah, this one is precise, but the precision is hidden in here.
exactly.
And
as soon as you are using homeomorphic, it's fine.
Pardon?
As soon as you are using homeomorphic.
Yeah. But I mean, so this is indeed precise, right? But all the precision is concentrated in this term, homeomorphic, which I will not elaborate upon. Alright, this is deep stuff, and we'll just look at some examples, and these examples will provide us with an idea as to what that could mean. And we are not really doing mathematics here. So here are examples of one-dimensional manifolds. For instance, lines are one-dimensional manifolds, or circles, and there are many more. Now let us look at a circle. Here is a circle. And this is a one-dimensional structure. This is something I have drawn on a two-dimensional surface, but intrinsically this is a one-dimensional object. Because imagine you were an ant, and the ant looks like a dot now, living on this circle. You can only go forward or backward. And that is to say, you're basically living on a line. This line happens to be sort of bent and end in itself, but this is a one-dimensional structure. It is embedded in 2D. This is a two-dimensional object, but intrinsically it is just one-dimensional. Right? This circle is often referred to as the one sphere. This S has nothing to do with the state space we just discussed, but this is the one sphere. And again, why is this intrinsically one-dimensional? Because if we do know the radius of this circle, and let me introduce like some zero line here, we do know the radius, then one parameter is enough. Let's call it, I don't know, angle phi. One parameter is enough to indicate our location on the circle, if we know the radius. If that is a given piece of information, we just need one parameter, because this angle phi can be large or can be small. Well, given the radius, we just have to look at what is the angle of rotation on this circular structure, and we can immediately say where we are. Intrinsically one dimension. Now, what is it to say that this is a structure, a manifold M, where each point on this manifold, and I'm just indicating a couple of them, has a neighborhood that is homeomorphic to the, in our case, of course, one-dimensional Euclidean space. Now that is basically to say that for every point on this manifold, the tangent here is a line. This line is a one-dimensional Euclidean space. If we are at another point, then again there is a tangent, it's supposed to be a tangent. And in a very tiny neighborhood around this point, we cannot really distinguish the fact that we are on a circle or on a line. And this is actually something we have to deal with in everyday life, and because let me give you some examples of two-dimensional neighborhoods. Examples of two-dimensional manifolds. Manifolds, not neighborhoods. Manifolds are planes. Right. Flat planes are two-dimensional manifold. Planes or surfaces of spheres. In that sense, like this circle is the surface of the one sphere. And now we see that we are actually, we have to deal with the fact of manifolds in our everyday life. Because the surface of a sphere could be the surface of the Earth. How do we know that we are living on a giant ball? From just looking around in this room, it's very difficult to say, right? Because the floor of this room is this like perfectly flat plane. Of course, it ends over there. But locally, like in a very tiny neighborhood of where I'm standing right now, everything is flat and Euclidean. Right? So this is the difference between, I don't know, a vector space and the manifold embedded in that space. We are living in three-dimensional space on a ball that is embedded in this three-dimensional space, racing to space. It's a planet. It's a very huge thing in comparison to each of us. So we are like the ants on this circle. We are sort of like tiny things on a huge ball. And if we look around in our immediate neighborhood, everything is flat. And we have to, you know, take huge steps back to see that this thing is actually curved. And so we are living on a manifold. Why would I talk about all of this? The problem we are facing, and we'll see that later on in game AI, is if we are given lots of data recorded from within a game, and we are trying to use machine learning algorithms to create behavior for game characters, it would be a good idea to try to figure out from the given data, like what is the structure of the game world. Because once we know that, we can, behavior of a game character might actually depend on where the game character is located within a game world. So for instance, if you are thinking about some 3D game where you can walk up some mountain and probably jump down that mountain, if that leads to your character's death, you would try to avoid that. So your behavior on top of the mountain might be different than your behavior on like, the bottom of the mountain, where you can move freely, but if there's a steep ledge, you might want to try to avoid jumping down that ledge because otherwise you drop to your virtual death. So behavior of game characters might depend on where they are located in a game world. And so therefore, a problem we might study is trying to understand, given lots of recordings of what people do within a game or game characters do within a game, can we learn from this data how this game world is structured? If we know that, we can then, in the next step, think about, okay, now that we know that, how can we come up with ways of programming behavior depending on where we are? So, the question we are going to study today is the following. Given a set of observations, and I'll call them vector x1 all the way to vector xn, and this time we do assume that these are m-dimensional vectors. Again, of course, for the example we've been looking at, m was 2, but in general we have some m-dimensional data. Can we identify the manifold S, this is in the configuration space, so let me fix this here. So we are given some data, which of course is a subset of the configuration space, which in itself is a subset of the m-dimensional vector space. So, you know, player could be anywhere within this game world, so configuration space might be something, but then in fact player is not anywhere but sort of confined to some special locations, can we identify this manifold as the data reside on. And again, when we've been looking at the configuration space and the data in this example, we would say, okay, this is a circle, but it's of course a degenerate circle because it's not a perfect circle. So in that sense, we have to be very, very careful when we talk about manifolds here. Machine learners do it anyway, right? They say, oh, this is basically a circle. For a mathematician, this is of course not a circle, but something blurred that could be a circle. We nevertheless call this a manifold. We can pose this question in a different manner. We can say, and this takes us back to the games, can we learn a state space representation? State space representation given observations of states players are in. Given observations of states players are in. This is the configuration space, and we observe states. And our question is there a structure in this set of states? Can we detect, recognize, and learn this structure? And if so, can we then later on use it for interesting things? Okay. Yeah, can we? Let me try the black one again. Some player trajectory, and I am, distorting it a bit, whatever. So can we learn a state space representation given all these states? Player has been running around in a circle. Your turn. We could cluster it and then say that we represent all this data in terms of the clusters we have found, right? So we could run k-means clustering on this, and that would probably provide us with clusters like this, and each of these clusters would have a centroid, and then we would say, okay, this state space is now represented in terms of 6 centroid vectors here. Yeah, that is okay. Could work. We saw that we have to be careful, but why not, right? So we could run k-means. But of course, we may then have found prototypical states among all the states we have observed from, say, recording the activities of a player. But we do not know if this state is more similar to this state than to this state. We just, very difficult. Okay, we can compute distances and say, okay, this one is farther away from that one. But the fact that the player has been running around in a circle is lost when we just look at these centroids. Now, we could try the following. Here are our observations of what the player did. And then we could come up with the freakish idea of computing a nearest neighbor graph given these points. And basically, for every point, we would connect it to its, say, L nearest neighbors. So L, in this case, L nearest neighbor graph, and here we have chosen L equal to 3, and this one whatever, like so, and whatever, you know, we could turn this into a graph, the data we are given. Right, we just choose some L, have a graph. Now we have a graph, then what can we do? Spectral clustering. Oh. Would work beautifully. Probably we would get something like, I don't know, this is a cluster, this is a cluster, and this is a cluster. Whatever. This is great because now we have clusters that look more like the underlying trajectory data. Yeah, but still, you know, still we have lost something. And now it's time to look at yet another idea. So here is the data we are given. And the idea I'm going to propose right now is the following. We initialize a codebook. And that is just a set W of codebook vectors W1 up to WK. For instance, I don't know, here is one of them, here is the other, here is yet another one, maybe like so. So 4, k is equal to 4 in this example. Yeah?
What is the correlation of this codebook with the points where? So
None at all.
So one point could be at the
Let me, we have one here. Yeah. I would not, in practice, advise of choosing them arbitrarily, but I would pick 4 out of the data points we're given. Mm-hmm. Right? So therefore I will erase that one again, but you could do it. I would not advise you to do it, so basically pick k points out of the n points you are given. Once we have initialized that codebook, we can run the following algorithm. So this is the first step. Now, for t equals 1 up to some t max, we do the following. And this t max usually is large, so I don't know, 10,000 iterations, whatever. We first sample a point x, for instance, say this one. Right. This is one of the data points contained in our set of observations. And then we determine the codebook vector that is closest to this point. Right. In our case, it would be this one, obviously. But this is the closest codebook vector to the current sample point at iteration t. Mathematically, we write determine the right closest point. Yeah. So we determine the closest codebook vector to the current sample point. And that is, we are interested in the index I, which is the arc max over all j, distance between codebook vector wj and sample point x. Right? When I write this, what I mean is, so for all the codebook vectors, j equals 1 up to k, we compute the distance between the codebook vector and the current sample point. And for one of these, hopefully the distance will be the smallest. It can happen that there are two at the exact same distance. We don't care that we break ties, throw a coin, whatever. But in general, one of them will be the closest. And the index I of that codebook vector, that is the one that minimizes this expression, is the index, well, we are looking for. Max, oh boy. Oh boy. What happened here? It's your job to tell me like these. So we're looking for the arc-min. Arc-min. Okay? Good. Now, once we have found that one, and in our example, it's obviously this one here again. Then we update this codebook vector. We update here, okay, I have time indices. Codebook vector I. So at the next iteration, so at time t plus 1, codebook vector I should now be codebook vector I as it was at the current iteration, plus some number eta, this is the Greek letter eta, which depends on the iteration we are currently in. So it's eta of t times the vector from the sample point x from vector x, from w to this vector x. So let me draw this vector and then it becomes clear. So this thing here is this vector, right? This here is a vector that points from this codebook vector wi, which is the closest to the sample point. It points from the codebook vector to the sample point, and we shift the codebook vector in this direction by some amount eta, where this eta is a number between 0 and 1. And that is to say, we move this point a fraction along this line. So it would end up, say, here. In that sense, we have updated this codebook vector. We look at this thing here, at the wi that will be determined using this expression. We look for the codebook vector that is closest to the current sample point. This wi is also called the winner. Among all the codebook vectors, this one is the winner because it was closest to where we are. And I just want to note that if we look at this update, so wi plus eta of t times x minus wi, we can write this as 1 minus eta, I'm dropping the dependency on t, wi plus eta x. And this tells us, if eta is a number between 0 and 1, that the updated vector, so at t plus 1, the codebook vector wi at time t plus 1, is a convex combination of the wi at the previous point in time and the currently sampled data point x. So by means of this update, we will always move the codebook vector again along this line segment between its current location and the sample point. And this is why I would suggest never to initialize the codebook vectors outside of the data, but pick some of the data points, because we can then see that by means of these updates, the updated codebook vectors will never leave the convex hull of this data. Right? Like these updates will never cause a codebook vector to eventually reside here if we initialize them from within the data. Because
but,
these.
But they can leave the data.
No, they cannot. They can end up in here. Yeah, yes. But this is why we have this beautiful T here. Yes, that can happen. Right, it's not desirable, but they can never end up outside of the convex hull. Right, this is because of this convexity property of the update here. Well, let me elaborate on that T. So. I note that one should choose, and now here is a fancy term, the learning rate, and this is this eta of t, such that it decreases over time. Right? That is to say, at the beginning of this for loop, we carry out brutal updates. We sample some data point, look for the closest codebook vector, move it along the line between the codebook vector and the sample point, and probably go quite a distance. Right? Is this number between 0 and 1, so we'll hardly ever go the whole distance, but make a huge step. And then over time, these steps decrease. The hope is that at the beginning they reside somewhere, and then by brutally updating their positions we sort of distribute them across the data, and then once that has happened we only do tiny updates so that they don't move like from here to there again or whatever. And therefore we would hope
it's like fine-tuning.
Yeah. At the beginning they will move like brutally around, and then towards the end of this will just tiny minuscule movements. And by doing this, one hopes that they will never end up here. There's no guarantee. Yeah. There's no guarantee. Actually, I gave Mr. Thiel a video to upload on the YouTube channel, which demonstrates how a neural gas, something we'll talk about in a minute, is growing, and there you can actually see this behavior. There's a video that demonstrates this behavior. So, should decrease over time. For instance, we could say that this eta of t is given by some initial value, eta at 0 times 1 minus t over t max. So this one will decrease with time. And I don't know, we can make this eta 0 equal to 1. This is a function, this decreases with time. Okay, we can do much better than this, because this is just k-means clustering in disguise. This is just k-means clustering in disguise. We are placing centroids using a different way of doing it, but it is just another centroid clustering algorithm. And this brings us to what we want to study today. We can do better. Let's look into the idea of self-organizing maps, also called SOMs. Who has heard of this before? Okay. Okay. Yeah, I was fearing as much. I don't know, for those of you who are taking the machine learning lectures at the University of Bonn, has not been done there.
No.
Okay, great. This is awesome because this will be fun. Let's see what a self-organizing map is. Color has no semantic, it's just the pen is probably more readable. A salt. And I will do something crazy because typically it's said that this is a type of neural network used in unsupervised learning to fit a low dimensional, and I put this in quotation marks, fit a low dimensional manifold into high dimensional data. This is goes back to a guy called Kohonen, say in 1982, and then Ritter and Kohonen in, that was 1989, basically nailed it. And this is used for clustering. It's used for dimensionality reduction and for data visualization. Okay, and usually this is introduced in the context of neural learning, which is a bit of a problem for us today because we have not talked about neural mechanisms for machine learning, but we don't have to. We don't have to because, as it turns out, these self-organizing maps are nothing but labeled graphs. So I will introduce them using the language we are already familiar with. And that is the language of graph theory, in particular the notion of a labeled graph. So here is the idea. Say you are given data, let's call it a set X consisting of data points, vectors x1 all the way up to xn. And again, each of these data points is an m-dimensional vector. This is what we are given, and what we are trying to do is to fit, and I put it in quotation marks, because how do we fit a labeled graph? But this is what we're going to try to do. A labeled graph, so let's call this one G, of course has vertices, edges, and a vertex label function, which I should call vlog. We do assume that there are v1 all the way up to vk different vertices. Again, there are edges, which is just among some of these vertices there is an edge, so we have edges as a subset of the Cartesian product, and this vertex labeling function vlog takes a vertex and maps it to an m-dimensional vector, so log for location, right? Now, in the context of neural networks and machine learning, these self-organizing, and nobody says that they are labeled graphs, but they are, right? But typically the vertices are called neurons. So I'll, just this is a set of neurons, and I put that in quotation marks as well, because it's of course not the kind of neurons we have in our brains, but computationally we can think of them as neurons. The edges are connections between neurons. And these vectors that are being assigned to the vertices, this is a function that maps the set of vertices to m-dimensional vectors. So for every vertex in this graph, we have an m-dimensional vector, and these things are called weight vectors. And I am just introducing this here so that you know these terms if you read up on this, because this is the terminology that is typically used. But to us, a self-organizing map is just a labeled graph, because that is familiar ground, that is what we are comfortable with. Okay, and there is not much to be said. I will just write down the algorithm, and then we discuss what that does, right? It's difficult to derive that from a theoretical point of view. This is much better than like just, dive into practice. Here is the self-organizing map learning algorithm. And this is something I insist on, you don't find that in the literature, but this is how we do it, begin by first computing a distance matrix, D, which we compute from the graph we are given. So we are given this graph of k vertices with edges between them. We haven't talked about how to choose these edges, but there is a graph. Each of the vertices is labeled with a vector. Now we compute the distance matrix D such that its ij entry is the distance between vertex I and vertex j. And I insist on that this is not the distance between the corresponding vectors that are attached to vertex I and vertex j, but it is the path lengths between these two vertices, right? So this is the path length of the path. Let's use path length from vi to vj. So we begin by doing this, and then we have a for loop where we initialize, this is for I equals 1 up to k, we initialize these label vectors, or weight vectors in the terminology. So for every node in this graph, we randomly initialize its label vector, the vector that is assigned to that node. Right? I would again suggest to, in practice, choose these initial weights from the data we are given. Well, you can randomly, whatever, does not matter. Okay, now I need a bit more space. So I'll erase these two preparatory steps. And now, we have another for loop over, say, t equals 1 up to some t max, and that has to be chosen large again. Just as we did before, we sample a point x in the data set we are given, and we determine the winner neuron, let's say, it's a stupid term, vi, where, just as we did before, this I is the arc min over all the j, wj minus x. This is just what we did before. And the difference is in this update. So once we have determined the winner, we update all weights. This is not just the winner. We now update all of them. And what we do is that each weight vector vj, which is assigned to a vertex vj, at time t plus 1 is supposed to be an increment of where it was previously, namely plus some eta of t times e to the, let's say, minus 1 over 2 dij over some sigma of t times this x mean minus wj at time t. Okay, so in contrast to what we have done just before, we now update all the, say, codebook vectors, all of them, not just the winner, all of them. And this is very similar to what we did before. We have this learning rate eta of t again, which can be chosen as we did before. But here is something special. We now also have a factor that depends on the distance, the topological distance, that is the number of steps in the graph between the winner neuron and the neuron we want to update. And of course, if this is the winner neuron, if this j equals I, then this is 0. Right? So we can do this. This is no problem here. But if this is not the winner neuron, we look at the distance between the neuron we want to update and the winner neuron. We scale that again by some factor that depends on time, and then multiply all of this with this vector pointing from where we are right now to the data point. So this is just one additional factor in this update, and the update is done for all of them, not just for the winner. This is the difference here, right? And the very crucial difference is that the update depends on the graph structure. Depends on the distances within the graph. And again, this sigma of t, so this eta of t can be chosen as we did earlier, right? And this sigma of t should also be a function that decreases over time. For instance, could be chosen as sigma at some time 0 times e to the minus t over t max. There are many functions that decrease over time. This one decreases quickly. Right. Now, what does this do? Why would we bother? What does this do? And this is, it can only be understood from looking at an example, but when we see the example, it's immediately clear. And we'll look at two examples. The first one is very close to our problem for today's lecture and actually to the next project. Let us consider a circular self-organizing map that is a graph that looks like so. I don't know, 5 9, I don't really care. This is also a fancy term is a circular path graph. Right. Every every node has degree 2, and this is closed. It's a circular graph. And let us again pretend we have a configuration space, and in this configuration space we have observed a player running around. So basically the state space is a circle. And now we do want to fit such a graph into the data we're given. And at the beginning we randomly initialize these nodes. I don't know, make it like so. Right, this is, we have randomly chosen some weight vectors, but these weight vectors are assigned to vertices, and between these vertices there are edges, and therefore this looks like so. That could look even crazier. All right, let me make it even crazier. This is not crazy enough. Make it like so. Something that is really not at all reminiscent of the data points. But, and this would be, say, at time 0 when we have initialized that. Then this algorithm proceeds, and at some point throughout the iteration of the algorithm, so I don't know, some ti, the situation may already look like this. These things have moved, right, because we update their locations. But if one of them is the winner, not only the winner moves, but it pulls all the other neurons sort of also into this direction because of this here. Right? And we do this for all the neurons. So they all move in every update. And if we do this, you know, a really long time, then in the end we stand a very good chance that this graph will have learned, or this self-organizing map will have learned the topology. In the end, this thing may look more or less like a circle. Typically it would do. You will have the chance to do that for yourself. Okay, this was somewhat trivial because if we look at the data, we know that it is a circle embedded in a plane. Usually we don't know that. Of course, with respect to the problem of learning locations within game worlds, this is easy because at max 3-dimensional data we can visualize 3-dimensional data. We have an idea as to what kind of topology that is. In very high-dimensional spaces we can hardly visualize the data, so a priori we don't know what kind of graph topology to choose, right? And so therefore let us consider another example, namely a regular lattice is another fancy term for something like this. Right, this is a grid graph. It's also called a lattice. Let's see what happens if we were to try to fit such a graph into the data we are dealing with today. So we have something, and the same, and again, the situation at the beginning, at some time during the iteration of this algorithm, and hopefully at the end of this algorithm. So at the beginning, you know, we randomly initialize 9 points, 1, 2, 3, 4, 5, 6, 7, 8, 9, and they, you know, are a lattice I can not really draw this. I could, but I don't. If, you know, this, there are 9 points, and one of them has 4 neighbors, 4 of them have 3 neighbors, 4 of them have 2 neighbors. They form this sort of regular lattice, but the points are located somewhere, and these edges are all over the place, right? But one of them has 4 neighbors. Let's make it like so. The others have 3, and others have 2. But we cannot recognize the lattice here. Now, after this has begun to run, and these things begin to move and pull their neighbors with them, at some iteration, it may actually look like this. I don't know. Like so. Yeah, this one would work. Here we can recognize the lattice. Right, they have moved, and now we can actually see this grid structure once they have moved. And upon convergence of this thing, it may look like this. I don't know. And here we see that, well, obviously this is not a really useful representation of the data, but we have started this algorithm with a graph structure like this. And then the algorithm begins to rearrange the locations of the vertices, like rearrange the weight vectors. And they will begin to sort of appear at suitable positions within the data, but the edge structure may not make sense, right? Because, you know, the data we are dealing with in this example is not reminiscent of a regular lattice. It's a circle. But nevertheless, we can fit a lattice into that. The algorithm happily does so. And this is what we might end up with. Right? And it may not make sense. It may not make sense. And this is a problem here. This is a problem. This is an extremely powerful idea. This is a very interesting algorithm that performs clustering, because, like, you know, once these neurons or vertices are located within the data, we can use that to, you know, argue, okay, all the data points in the vicinity of this neuron here would belong to that neuron, would be represented by that vertex. Can use that for clustering, right? Can use the graph structure to, I don't know, chop that. We can either do this like now, because all the vertices have a vector attached to them, we can do geometric clustering, or we can do topological clustering using spectral clustering. But if we are not sure what kind of a graph structure to use, then something like that can happen. Right? In this example, of course, it would be best to choose a ring graph. We know that. We can look at the data. We are good. In general, we don't know that. Very powerful idea, but it suffers from the fact that we have to choose a graph structure when we start this algorithm. And therefore, we can do better. We can look at yet another approach in the realm of neural learning that basically does exactly the same, but differently. And yeah, we started a bit late, and that's, you know, I'll briefly walk you through it. We can do it. This one is called neural gas neural networks. Neural gas. That goes back to Martinez and Schulten. in the early 1990s, 91, and the thing we are going to look at today is actually called growing neural gas, and that was proposed by a guy called Fritzke. In 1995. And the idea is exactly as in our previous setting. We are given data. So idea, given lots of data points in some m-dimensional space. We want to fit a graph, fit a labeled graph, I'll drop that. Fit a graph, G consisting of vertices, edges. Then we have a vertex labeling function called vLocation, another vertex labeling function called vError, and an edge labeling function called EH. So, yeah, we have lots of labeling functions here. That is, there will be two types of vertex labels and one type of edge labels. And again, this is, we have to look at the algorithm and then we know what it does. This is difficult to derive theoretically, you have to jump into it. So this function vLocation maps vertices to m-dimensional vectors. And from now on, instead of writing vlog of vertex vi, I'll just write vector wi. Right? So for every vertex vi, we have a function that maps this vertex to an m-dimensional vector, but I'll reduce notational clutter. I'll just write wi to indicate these. The error function maps a vertex to a real number, and I will write it as so we have the error function that maps vertices to real numbers, and instead of v_err of vi, I will just write error of vi, and then we have this edge labeling function EH maps an edge to a real number, and again instead of EH of some edge E, I'll just write H of E. Right. So this is the kind of graph we do want to learn, and here is how that works. The crucial difference is that we do not select a graph structure upon starting the algorithm. Here the idea is to learn the graph structure and the topology like at the same time. And therefore, the initialization is slightly different. So here is the growing neural gas algorithm. We begin by initialize this vertex set. We don't provide a set of vertices. We just say at the beginning there are just two vertices. Let's say V1 and V2. And the set of edges contains just one edge, namely from V1 to V2. So at the beginning there's just two vertices and one edge in between. And we also initialize the weight vectors attached to every vertex. Random sample X in this data set we are given. And what we are trying to achieve here is that It could happen if we have like 1000 data points and we randomly sample 2 of them that actually we pick the same one twice. Can happen, you never know. We want to avoid that, right? So if that happens in practice, make sure to catch that. So make sure that if you randomly sample 2 of the data points and assign them to the vertex weight vectors, make sure that the 2 vertices have different vectors, right? We also, in the initialization phase, set the error of both vertices to 0. This is the error function. We initialize it to 0 for both vertices. And we initialize the age of this edge from V1 to V2 to 0. Right, this is the initialization. Just 2 vertices, 1 edge. We pick 2 random locations to assign them to the vertices. Make sure that it's not the same location. Set the error of both vertices to 0 and the age of the edge. And now we have the trusted for loop over a long time again. And this time, by long I mean long. So we have for t from 1 up to some t max, which is large. It's typically in the at least area of 10,000 or more. And we sample a point. Sample a point x as we did before, right? We determine the 2 closest vertices, say Vs and Vr in the current set of vertices. Well, at the beginning we only have 2 vertices, so at the beginning the 2 closest will be the 2 we have, but over time vertices will be inserted into this graph, so over time we'll have to look for the 2 closest ones. I could write it down in the sake of time. I don't really, you compute the 2 vertices whose weight vectors are closest to the current data point x. Determine the 2 closest vertices. We call them Vs. This is the closest one. Vrs, like this is first and this is the second closest one. We update the error of the winner, Vs, this is the one that is closest, and just simply to error of Vs is the previous error of Vs plus, say, the squared distance between the weight vector of vertex Vs and the sample point. And then we move the winner Vs towards this sample point, basically just as we did before. Ws will be updated to Ws plus some constant delta W for winner, x minus Ws. Right, and of course this constant delta W is again a number between 0 and 1. Interestingly, it does not depend on time. It does not depend on time this time. This is just a constant number which remains the same over all iterations. So we have moved the winner, and next thing we have to move, it's a graph. So we move all the neighbors. move all neighbors, how do I call them, Vn of Vs towards this current sample point. This is basically to say we update their weight vectors. These are the neighbors of the winner to Wn plus some other constant delta n for neighbor x minus Wn. This is again a number between 0 and 1, and it is constant. It does not change. We're almost done. This is lengthy, but it works. Now, we have sampled a point, determined the two closest vertices to that point. We have increased the error of the closest point. We have moved the closest point. We have moved all its neighbors. Next thing is we increment the age of the edges. Increment age of edges incident to the winner vertex. That is, we set that the age of the edge Vs Vn is, I just make it fuzzy, increased by 1. So in the sake of time. So we increase the age of the edge between the winner neuron and its first neighbor by 1. We increase the age of the winner neuron and second, and all its neighbors. We do this for all the neighbors of the winner. Now, why did we determine the closest and second closest vertex to the current sample point? Becomes apparent now. If vertex Vs and Vr are connected, then we set the age of the edge between the two to 0. Age between Vs and Vr is 0. This is crazy because in the previous step we have increased the age of all the edges, Vs and its neighbors, by 1, and now one of the neighbors, if the second closest vertex is a neighbor of the closest vertex, now we'll set this age to 0 again, right? This is on purpose. If they are not connected, so else, we add an edge between Vs and Vr. So that is to say we increase the set of edges by one element, Vs, Vr, and the age of this thing, Vs, Vr, will be set to 0. Here at this point, for the first time in this algorithm, something happens to the graph, not just to the labels, but here we insert an edge. Right? Now, this continues. In the next step, we check if there are edges E in the current set of edges whose age exceeds some greater than a max. So we have a maximum age. If one of the edges in the graph, through all these iterations, has achieved an age that is now larger than a preset maximum, we remove this edge. Right? Remove them. If this causes if this causes isolated vertices, vi, that is after we have removed all the edges that have an h larger than a max, and if after this removal there is a vertex vi that is isolated, that is, it does not have any edges incident. We might have erased an edge to a vertex which only had one edge. Now it might be gone. If that is the case, we remove that vertex as well. Remove that. This is therefore the second time something happens to the graph. Right? We might actually remove nodes from the graph, and we might remove edges from the graph. So, and now we are almost done. Let's see what we got. How do we actually insert nodes? So far we have inserted edges if need be. We have removed edges if need be. And we have removed vertices, but we have not added vertices. And that is the final thing. So if we are in an iteration that is a multiple of some constant lambda. Lambda could be 100. So in the 100 iteration, t mod lambda would be 0. In the 200 iteration, that would be the case, right? And if the number of vertices in the graph so far is less than some maximum number we would allow, n, right? Then we create a new node. Create a new node. Let's call it Vn. Vn as follows. We determine a node Vu as the arcmax, and this time I mean it, arcmax, over all nodes in the graph. And we look at the error. So we look at the node in the graph which at this point in time has the largest error value attached to it. Right? And we look at another node, say VV, as the arcmax of all the neighbors, Vi, neighbors of Vu, where Vi. Once we have found the node with the largest error, we look at all its neighbors and determine the neighbor with the largest error. Right? And then we create a new node. Yeah, it's on the movie anyway. So then we said Wn, so the weight vector of this new node will be the weight of U plus the weight of V divided by 2. So it's exactly in between the node with the largest error and its neighbor with the largest error. Right? And we set the error of this node with the largest error, du, to some constant alpha times the previous error value. Alpha is again between 0 and 1. We do the same for this vertex VV, alpha times VV, and we compute the error of this new node, Vn, as simply the error of this node, Vu. This is really seriously now the last thing we do. Now we have a new node. It needs to have edges, right? We create an edge. I'll just write it down. Create edge from VU to the new node Vn, and another edge from Vn to this neighbor of VU with the largest VD is there, largest error, and we remove the edge between VU and VV. And then, very finally, this is the last thing we do in this for loop over T, decrease the error of all nodes. And we set error of Vi is the error of Vi minus some constant beta times error of Vi. Okay, so that's it. That is the neural gas algorithm. And you have to see it running. And I have uploaded, or I hope Mr. Thiel has uploaded a video as to how this actually works over time. And you see really like this graph bubbles over the data and increases adds new nodes and edges, and then eventually it really captures the topology and geometry of the data. You have to watch it in the video which I uploaded to the site. Yeah, this thing is extremely powerful. There are a lot of ideas that make sense. In particular, this idea of I don't know, increasing or decreasing the age of edges, and this can be thought of mimicking what is called Hebbian learning in neural network architecture. So this is indeed rooted in neural learning, but from looking at all of this, in the end, this is just a bunch of heuristics. And it includes numerous parameters, like what is H max, what is this lambda, what is the maximum number of nodes, what is delta W, what is delta N, what is alpha, what is beta. Nobody knows. This is a craft and not science, right? But you have to implement it in the next project, and this is a great opportunity for you to see what happens if you choose different parameters, and you'll see for some it will work and for some it won't. And there is nothing I can do about it. This is just how it is. So this is extremely powerful, but it crucially depends on how you choose all of these parameters, and nobody can tell you how to do that. I provide an example parameterization on the project sheet so you can actually see it. Yeah?
In the case of classification problems,
yeah.
for example, they have a cross-validation
yeah.
to pick the right parameters.
Yeah, yeah, yeah.
So is there any way to play around with those parameters in automatic
Sure.
way?
I mean, okay. So his question is, can we not automatically determine? Yes, we can, right? But we have 7 or 8 of them, and we have this T max. And in order for this to work, this at least requires, you know, even for this simple example with the waypoint graph on the project sheet, I did it for 10,000 times. And in Python, you know, this is one of, you know, network X is really beautiful because you don't have to worry about all these labeling functions. It does that automatically, sort of. But it takes like 5 minutes just for one parameterization.
Oh.
And this is exactly the problem here. Of course you can run this like 50,000 times with 50,000 different parameterizations, but that will take a lot of time, even for stupid, simple two-dimensional problems such as the one on the project sheet. You could, you know, run a genetic algorithm on the parameterization and see, you know, what, of course you can do that, but there is no real principled way, no obvious way of how to do that quickly. All right. That's all for today. Are there any questions? Next week is indeed no lecture at all because it's this Pentecost break. So we'll see each other again on Monday in 2 weeks. See you.